So we're doing the exam next Thursday. It's the day before the break. Yeah. All right. So I actually left this out last lecture, so I'm going to put it in here. So we're in Diamond's data set again. If you look at the response, which is price, looks like this. This is a very right skewed distribution. So most diamonds aren't worth so much. Some diamonds pretty valuable. There's more diamonds that are not worth so much than diamonds that are valuable. Hence the skew. So this is just an interesting fact about diamonds. Well, here's the thing. If you're modeling a phenomenon, does it make sense to model an extreme phenomenon or a more regular phenomenon?
A more regular phenomenon.
Why would that be?
Isn't it the law of large numbers? Where, oh no, sorry. The mean, you're most likely to get the mean. The most frequent, in a static system, you're more likely to get.
This is a hard question. It's a hard question. So usually the answer is you want a more regular phenomenon. Because think about this in a linear regression context, right? Let's say you've got one predictor and you're looking at the y. X versus that y. With a very, very long tail phenomenon, you'll have very, very large outliers, very small outliers. So a regular phenomenon will look like this. So if you have something that looks like that, the line is going to, these points are going to be high influence points. Now, we never went over influence, but the influence is actually, could be measured from the projection matrix. It's actually the diagonal projection matrix tells you about the influence of each point. We never did in this class. It's a topic for like a more advanced linear model class. But the idea is that if it's far away from the distribution of, here's the distribution of x. It's far away from the distribution of x, and far away from the distribution of y, it could be highly, it's called points that are leveraged. It'll leverage your regression. Basically means the whole world bends to accommodate those points. You can think of it like that. So do you want the whole world bending to accommodate these extreme points? Probably not. If it's a complicated model enough, if it's a complicated enough model, then what it's going to do, it's going to draw little micro regions around each place and fit little models to that. We're going to get there with machine learning. Usually speaking, like, you want a nice distribution for y. I'm not giving you any real reasons for this, but empirically, it seems to work out that you want a nice distribution for your y. Also, in terms of, if you could think, models usually are elaborate ways of taking smart y bars. You saw that in your homework, right? Linear model is just taking y bar of things. Linear models take averages of little spaces. So you have average of little spaces, and you've got a few small values and a big value. What's the average going to do? It's going to move up to the big value. Same thing as like what I'm saying here, leverage points. Like this line can go like that, even though the line should be like this, kind of. Right? That's kind of the idea. So you don't want there to be extreme values in small samples. Right, did I make enough heuristic arguments here? Okay, what would you do with this variable? Let's say I want to make it more regular. Economists. You know what to do with the economists. More,
Shorter tails.
less extreme.
Make a cutoff.
How do I make the big values smaller and the small values stay the same, give or take?
Take
take a log. Let's take a log. Thank you, Jan. So, log transform long tail. It's easier to model that long tail. I call this craft lore or triplet trait. So let's take a look at the log. So all I'm going to do is just log the price in here. Why is this slow? How does that look? Is there extreme values now?
What is wrong with that 1 point?
I don't know. I think they're just missing a whole bunch of diamonds somewhere. For some reason, people don't price diamonds in that range. There's like a taboo to price diamonds between those two. I don't know. Maybe it's an artifact. I don't know. It is. I agree. It's strange. But forget that. Just forget that artifact. What do you guys think about this? Is it more regular than this picture?
It's more centrally weighted.
Right. It's more bell-shaped. So here's what we're going to do. We're going to fit a linear model to price and a linear model to log price using the same features. And then we're going to ask what's the R squared in both cases. And then we'll see if I'm right. So first of all, you notice that we have really good models for, in terms of variance explained, we have very good models. RMSE, plus or minus $2,000. That's haggle territory anyway. Right? You go to the diamond dealer, the guy's like 10. I'll give you 7. 85, all right, deal. So it seems like we're able to predict the price of diamonds, which makes sense. You know how big it is, you know how clear it is, you know how it's cut. You should be able to predict the price of it. It's kind of like a man-made phenomenon, right? Man-made phenomena are easy to predict. Non-man-made phenomenon, hard to predict. Yeah.
Why is there such a huge gap in? Oh, because we're not modeling it.
We're moving from 92% to 97% R squared.
But that's a huge difference, right?
Is it?
RMSE's.
Hold on. We're not at RMSE yet. This is a good test question, by the way. I love this question. Because there's so many ways to get it wrong. Okay. I moved from 92% to 97%. You must admit that's a gain. It's not a huge gain. It's like 5 to 10%. Pretty good. This is proof for, at least with linear models, without any fancy, squares or interactions or whatnots, you're better off modeling a regular looking phenomenon. Because you have less of this going on. This leverage idea, which is going to screw up your slopes. That's what I think is going on. Okay, now, let's talk about RMSE, which is these two lines here. What does this RMSE mean?
Oh.
What does this RMSE mean?
That's dollars.
Oh shit, I wasn't calling on you. I was calling on the class, and you raised your hand. What does 1130 mean? Anybody? I've only done this like 10 times. Jan, go.
That's one standard deviation above or below that line. Is one standard deviation is.
It's one standard deviation of the residuals.
Yeah.
That's the standard deviation of residuals. Modulo 1 over square root of n minus p minus whatever that thing, which is not going to make a difference if n is 50,000. It's basically the standard error of the residuals. So plus or minus 2 of them, if you believe normal theory, will give you a confidence interval the size of your error. So this model predicts plus or minus $2,200. 95% of the time. What does this mean? approximate percent, but what is it exactly?
17.55%.
Okay. Log is approximate. Okay. It's plus or minus 0.34 in log price units. Once you've changed the y, you've changed RMSE. So this is actually a really good reason for using R squared to compare models. R squared is scale invariant. You change the scale of y, R squared is still R squared. It's between 0 and 1. Percentage of total variance explained. RMSE, you change the scale of y, you change the scale of RMSE. RMSE is in the units of y, which is usually why it's so useful. But you change the scale of y, now you got to think in log dollars. That's harder. Moshe's right. Log of log x is approximately percent change in x. So this is plus or minus 34%. So you're off by plus or minus 34%. So if you guess $1,000, it could be as low as minus 34%. What's that? 600, and as high as, I can't do this in my head. It's gonna be higher than the 300. Yeah. You have a question?
I would just, what do you said that that R squared, it remains the same. You're saying that the...
Doesn't remain the same. The metric is scale invariant, which means that it always represents percentage of variance explained in y.
Okay. Meaning, it's not a matter of units, it's a matter of how much better it is than your method. Okay.
So there's no overfitting here because I didn't add features. If you go by R squared, this is a better model. And I think it's for the reason I described. Usually get some mileage out of logging y or squaring or doing something to y to make it look more regular. So there's a short downside. Now when I go to predict, what am I predicting if I use this model? Log price. But I don't really want to predict log price. I want to predict price. So we got to do log price to get the price.
Take the E.
Right. Here's the problem. Small problem. Which we're going to see in 621. Expectation of g of x is not equal to g of expectation of x. They're not the same thing. So if I take the log of the best guess, linear model returns kind of like the expectation. Or if I take expectation of the log, it's not going to be the same. Let's see. So let's predict. Here's the two predictions. This is for a random row. So I get $5,400 or 8.469 log dollars. I take the 8.469 and I exponentiate it, and I'm not going to get 5,423. I'll get something a little bit different. That's because of this. Usually speaking, you don't care because you're getting more juice out of using the log model. You're getting a better model. Okay. So if you like log transformations, there's a whole bunch of transformations that are really smart. So if you take a class in basic math stat, there are these really cool things called variance stabilizing transformations, where you take a transformation and all of a sudden the variance is always 1. Anyway, there's a lot of work that's done in transformation, and a lot of it is useful for prediction. But business as usual, you usually just log it. And if you have a left tail, you square it or exponentiate it. But log is by far the most common because so many things have a skewed right tail. Because usually modeling prices, a lot of things in the world are power laws. which means that 10 times, like, chess ability. Like, it's really easy. In chess, the amazing thing is there's always someone better at you in chess. Not only better than you, 10 times better than you. And then him, 10 times better than him. Him, 10 times better than him, etc. Like, you just, a lot of things work like that. Diamonds, you could always spend 10 times on the diamond. If you think your diamond's expensive at $10,000, you could just buy a diamond for $100,000. Think your diamond's expensive at $100,000? You just buy one for $1 million. You just keep going. You want to buy the crown jewels? Billions of dollars, if they're even for sale. So frequently, phenomenon look like this. And when you model them, you log them and get something a little bit more regular. Sometimes even people take double logs. I can take a log of this again, right? Let's see what that looks like. See if that. It's not going to help because it's already sort of regular looking. And now it's like more regular looking. Sometimes that's popular too. Okay, so going forward, I'm going to just use the log price for everything because it's going to result in better models. So what does this do?
It replaces price with log price.
Yeah, and it overwrites it in the data set. That's what this is pipe and overwrite. Yeah.
When we're doing our regression on on log y, that means that we're predicting our features to have a percent or a log change in y, not a log change in our features will be a change in y, right? Meaning,
Right, yeah.
meaning whatever the log term is the one that will be it's not reinterpreting the other ones, it's reinterpreting itself.
So if I have log y, so B1 is change in log y for a 1 unit change in x. So if I change x by one unit, ln y goes up by b1. So this is a percent change in y.
For a unit change in x, yeah.
So now let's do this one. So a 1 unit change in x will be a b1 unit change in y. But a 1 unit change in x is really 1 unit change in log x.
Wait, a 1 unit or a change in log 1, like depending on how you look at it.
Yeah, a unit change in log x. Now what's a unit change in log x? If ln x goes from 2 to 3, you multiply it by 2.713. That would be a unit change in log x, right? No?
Oh, yeah. Maybe doing e to the x instead of ln x would do something similar?
You want to do e to the x now?
Yeah, we did e to the x instead of.
Then you don't get percentage changes.
Oh, yeah, that's right.
So let's say a 0.1 change. So a 10% change in x would be a 0.1 times b1 change in y. Now, if you want to go crazy, percent change in x, percent change in y. This is really Econ 382 stuff, though,
Yeah.
right? So it's nice to review Econ 382 once in a while. It only matters for us if we could do something like this, manipulate a situation, get a higher R squared. That's all we care about. We just care about better predictions. We don't care about interpretation. Interpretations are stupid anyway. Your models are all wrong. That's the truth. Interpretations, dumb. At the end of the class, we're going to go over really what B1 means. You'll see, you know what it means? We're going to see it means nothing. It means very, very, very little. like the difference between an animal and a stuffed animal. You think you get an animal? It's really a stuffed animal. It looks like a tiger, but it's not really it. They're garbage. You know what's real? How to sample RMSE. That's real. That's real. How to sample RMSE. That's something. B. Garbage. Okay. So last time we spoke about cross-validation. Can someone remind us what cross-validation is? How about this? Can someone remind us what out-of-sample validation? How about this? What is validation? Let's start there. Go.
You split the data set.
No. What is validation? Before we get to out-of-sample validation.
Checking your model.
Checking your model. Seeing if your model actually works. If your model doesn't validate, model's crap. Right? Why do you validate your model? To ascertain if it's good or not. If you don't validate it, you have no idea if it's good or not. Could be great, could be terrible, you don't know. Okay, now what is out-of-sample validation? Joseph?
Checking your model on future data.
Right. So in a supervised learning setting, you fudge out-of-sample validation by making an assumption called stationarity and splitting your data set into something you use to build the model and something you use to check the model. And that thing you use to check the model is considered out of sample. Why is it out of sample? Well, you didn't see it when you made the model. That's as good as the future with stationarity, right? So it would be the same thing as asking the world for 100 more data points and seeing how your model predicts them. So there was a drawback to doing one split. So we talked about the size of the split, which is parameterized by this thing called k. So if k is 5, then you leave out 1 over 5, which is 20%. Here's the problem. Your 4 over 5 and your 1 over 5, the split can be very arbitrary and idiosyncratic, which means it's a very, very random estimate of what your out-of-sample performance will be. So one way of getting around that is to average over k splits. That's cross-validation, because when you average over the k splits, you're moving that split through each one, and then you're taking the average over all of them. The aggregate predictions you get at the end is a more stable prediction of your out-of-sample error. And also, you get this nice thing where you get to kind of see the standard error of each of those. You get the standard error of your out-of-sample error. So it's S sub SE. So you get SE1, SEK, and from these you get an S SE. So you get to see how stable it is. Okay, let's see an example of cross-validation for the diamonds data set. So first of all, I need k equals 5. I can do k equals 10, k equals 5. We've talked about how you just don't want it to be too low. 2 is the lowest. Lower than 2, like, is crazy. 2 is too low. Lower than 2?
Lower than 2 doesn't make any sense.
Right. That's true. Yeah, lower than 2 doesn't make any sense, you're right. And the highest it could be is n. Meaning you do this n times, leaving 1 out each time. So the world has seemed to converge on 5 or 10. So we'll just use 5. So here's a really, really clever way. I found this on the internet like many, many years ago, and I've been using it ever since. Here's a very, very clever way of creating the fold spec. So first of all, you need to randomize everything and call 1/5 of them fold 1, 1/5 of them fold 2, 1/5 of them fold 3, 1/5 of them fold 4, and 1/5 of them fold 5. Right? So here's what you do. You generate a whole bunch of random numbers. And then you use this function called cut, which is in base R, so what cut does is you feed in breaks, and everything within the first break gets a 1. Everything in the second break gets a 2. Everything in the third break gets a 3, and so on. So you feed it in 6 breaks, 6 breakpoints, and between the first and second number gets a 1. Between the second and third number gets a 2. Between the third and fourth gets a 3. Fourth and fifth gets a 4.
What do you mean by gets it?
It'll be assigned.
Meaning
I'll
the
show you, I'll
indices?
show you. It'll just be assigned the number 1.
So 6.
Well, you need 6 because that makes 5 buckets. The bucket's defined by tween. Yeah. One, A, B, C, D, E, F. So everything between here and here gets a 1. Everything here and here gets a 2, 3, 4, 5. So if I make a whole bunch of random numbers, and this is the min and this is the max, and this is sort of even quantiles, 20 percentile, 40 percentile, 60 percentile, 80 percentile, 100 percentile, then I'm basically taking n numbers and I'm assigning 1/5 of them to 1, 1/5 of them to 2, 1/5 of them to 3, 1/5 of them to 4, 1/5 of them to 5. It's ingenious, isn't it? So let's take a look at this. Here's what folds vec look like. Let's give it a 1. And if I table it, you should see about equal in each. Oh, it's exactly divisible by 5? Is that true? Oh, look at that. Nice. Anyway, it's essentially just taking 20% of them, throwing them into bucket 1, another random 20% throwing into bucket 2. You guys get the idea here? That's exactly what we want. So now here's what we do. We're going to do the cross-validation in here. So here's all the indices. Here's a place to store all our SEs. Here's a place to store all our predictions, out-of-sample predictions. And now we're going to iterate through all the folds. In each fold, I'm going to take out the test data. What is that going to be? That's every place in this folds vec where I get little k. Makes sense, right? Yeah, I'll show you what this looks like. That is random 20% of the indices in the diamonds data. And then, what's the training there? Well, everything else. So it's just the set difference of everything minus that. So I put test and train back together, I get 1 through n. This is my check for that. Now I build a model on just the training. Remember, price is now log, right? So all my out of sample stuff is going to look like standard error of log, so it's not going to look like dollars. And then I predict using that model built with the training data on the test data. That's my y-test. And I put it in the right place in my big y-test vector. Then I'm going to calculate RMSE now, which is basically, it's the real y minus my predicted y squared, summed, over the amount that I have, which is test indices, square root. That's square root MSE. Sounds good? A lot of work, right? A lot of careful coding. Now run the whole thing, and what you'll see is this is the results of the folds. Those are the RMSEs. This would be the average out-of-sample RMSE plus or minus the standard error, and you can see that the standard error is small. Meaning if you believe that they're independent, or believe that they're quasi-independent, this would indicate that your out-of-sample error is about 0.17 plus or minus 0.01. So it's between 0.15 and 0.19. That's how well you'd predict in the future in terms of log price. Now this is a little bit different. This is the aggregate. This is your overall best guess as to this and this are similar. This is your best guess of your out-of-sample error. You don't get a standard error for it. You only get a standard error for it within fold. This would be the aggregate over all folds. Maybe don't worry about that too much.
Yeah, I don't fully understand. Like I thought we just said that we had.
Okay. These are the best guess as the error only on 1/5 of the data. This is still the best guess as for only the 1/5 of the data. This is the best guess as for all the data, somewhat, maybe. I wonder what's a better estimate, this or this? Maybe I have to read up on this as myself. They're usually very similar. Taking the aggregate over all 5 folds or averaging all the 5 folds.
Oh, is it the difference between like a grand mean and mean?
Maybe. Yeah, grand mean and local mean. I don't know. They usually print out both, though. The aggregate and the average of the folds. Anyway. Any questions on cross-validation? How stable is cross-validation? You think it's pretty stable, right? So just remember these numbers. Well, I have them right here, so. If I change the seed, what just changed?
Your division of the set.
My division of n into 5 things. That is randomness in a cross-validation that is not integrated over. If I make different splits and I try it again, it will be different. How much different?
Hopefully not too much.
Hopefully not too much. Otherwise, the whole cross-validation thing isn't so good. So let's do this again. Point 0.17, 0.176, 0.178. What's our saving grace here? Why was it not that different?
Because our data is consistent and we have large amounts of it.
Large 50,000 data points. Yeah, there you go. 50,000 data points. It's not going to be too different. If it was 100 data points, it may be very different because the splits may actually matter. And even if you think you're getting around the splits mattering with cross-validating, it still matters. It's very hard to do this thing with small data. Very hard. May even be hopeless, yeah.
Can you repeat again what you did when you changed K? I mean, when you changed the C?
Yeah, so I started with a whole bunch of data, and I split it into random 5 groups. It's like just throwing them into 5 buckets. And then I do the model in each of those 5 buckets. But I could put into the 5 buckets a different way. And then a different way, and a different way, and a different way, and a different way. And if I come out with different answers each time, then there's a lot of randomness still due to the the randomness before was due to the idiosyncratic split. I'm trying to get around it by doing it 5 times, or rotating the split. But I still have the idiosyncratic splits. In this case, because there's 50,000 data points, the buckets basically, each 10,000 sample looks exactly the same. Because there's so many. Okay. So I've taught you a lot of libraries. We're going to learn another library now. So what do you guys want to do on the lab on Friday? Do you want to do new stuff, or you want to do old stuff?
Can we prepare for the test?
That would mean a vote for old stuff.
When will we have
Old
a chance
stuff?
to do?
Yeah.
When will we have a chance to do new stuff?
After the break. Because Friday is the last Friday before the break.
Will it be enough?
What?
Will it be enough time
To do what?
to do new stuff and then whatever new stuff we do after the break?
No, the new stuff wouldn't be on the exam.
No, that's not what I'm saying. I'm saying would we have enough time to do the new stuff in the lab? Like in all the new stuff in the lab? Or in labs?
Then you
Well, there's not that much new stuff. We haven't done anything yet. Right? So this MLR stuff will be new. Cross-validation, I think I put it on the... Did I put cross-validation in the previous lab? Where's the end? Okay, so you do cross-validation. You'll copy this code. We haven't really done anything yet. Maybe you'll log Y. It's not that much new stuff. Okay. So, here's the deal. MLR is short for machine learning in R. It's a very popular R library. It's becoming the standard for doing this type of stuff in R. What does this type of stuff mean? Building models, validating models. Selecting models, which we'll do next. Well, the support for model selection isn't as good as I thought. Anyway, you see how much code this was and the potential for bugs here? Cross-validation is a very, very standard procedure. It is totally standard. So why should you have to do this each time? Right? You should be able to hit a button and it just goes boom, do it for you. That's exactly the goal of MLR. To do all these really mundane tasks. Mundane and quotidian tasks. Anyone speak French? Quotidien.
Recurring daily.
You speak French?
No, GRE word.
What?
GRE word. Quotidian.
Is there in Espanol? It means like a daily, like todos los días. Yeah. In English, we also have the word quotidian, but it's only on the GRE. It's like an advanced word. It really means like, it means more than daily. It means like run-of-the-mill, common, commonplace. It doesn't actually mean daily, even though like that's where it came from Latin, or probably from Latin. K-fold cross-validation is a quotidian task. Building a model and validating, quotidian task, totally common. Why not, instead of writing this yourself each time, introduce the potential for bugs, and everyone can do it their own way. And this, although very good code, if I say so myself, is still hard to read. You have to read it and think about it. What the hell is set diff? You gotta think set diff. Okay, set diff. Like, it takes a long time. It should be just one button. One button. That's all. Enter MLR. Let's see if this installs. Otherwise, we're in a very, very, very short demo. Nice. That's what I like to see. Okay. So it splits the whole modeling enterprise into a few conceptual pieces. here are some of the basic pieces. There are more pieces if you want to get more advanced. We're going to get more advanced later. But this is what we've done so far. We first instantiate a task. A task means you give it a data frame, and you identify a variable you want to predict. And then you say, I want to use algorithm A with H. That's instantiate a learner. So the task is like the prediction task, and the learner is the algorithm you want to use. That's the A and the H. For example, OLS. For example, diamonds, data set, predicting, log press. And then you say, I want a type of validation. And then you press go. Seems pretty good, right? All right, let's see what we got. So we create a modeling task using the function make regression task. Now, inside the whole giving a data frame, giving a variable, once you give the variable, you need to say, well, if it's a continuous variable, it's a regression. If it's a binary variable, it's a
Classification.
binary classification. If it's a nominal variable, it's a
Category.
just classification, not binary, non-binary classification, or a multi-label. There's different names of that. We didn't do survival, but there's also survival. In this class, there's also probability classifier, sort of guessing the probability of an event if it's 0 or 1. We're going to get there towards the end of the class. That's logistic regression. Anyone seen logistic regression? Did you do that in 382? Good. Great. Okay, so we're saying make a regression task, use the diamonds data set, and I want to predict price. Then give it an algorithm. Make an algorithm. Make a learner. The learner, you need to know the lingo. This stands for regression LM. They're all coded as constant strings. So this basically says, I want my learner to be OLS. Boom. Validation. That's called make a resample description. I want to use cross-validation with k equals 5. Sounds good?
So crazy. Love this.
Isn't it great? Everyone loves MLR. And now you go boom, resample, and it'll crash. But that's okay, because it tells you, it's very, okay, here's the deal with MLR. I'll just show you something in a second. There's a reason to why I know MLR is this way. MLR is very, very, very careful with everything. Which means that if things aren't exactly right, it'll blow up. This is for your safety. Because if you give something a little bit wrong, and there's no warning or error or whatever, it'll just go through and you'll get some wrong result. So what it tries to do is it tries to be very, very careful and throw a lot of errors along the way. So here's what this error says. It says, hey, you've got ordered factors in there, and regression can't handle that. Now, is that really true? Can regression handle ordered factors?
In the homework you said it was a difficult problem.
There's two ways we spoke about putting in ordered factors into a regression or linear model context. What did we say?
Categorical binary.
Yeah, drop the orderedness, consider it nominal, and make dummies.
Or some.
Right? Yeah, that's what you did in the homework with the y bar A, y bar B, y bar C. The other way we're saying is keep the order
Make it some weird continuum.
and drop the category, which means you code it as 1, 2, 3, 4, 5. High, low, medium becomes 3, 2, 1. High, medium, low becomes 3, and then 2, and then a 1. So there are problems with both of these things. The problem with dropping the orderedness is that the answer will no longer respect the order. because it's just treated as like three totally separate things. And if you drop the nominalness and make it encoded as 1, 2, 3, then you're implicitly saying that the space between them is whatever the space you code them as. You could do 1, 2, 10, 1, 2, 100, 1, 3, 100. Then you have an arbitrariness at which to code. The default in R is just to treat it as a nominal. But MLR is very careful. It's saying, you need to make a decision. Make a decision right now. Cast it to numeric or cast it to factor. Okay, so let's correct it. Let's cast it to factor. So what does this do? I'm mutating cut to be a non-ordered. Ditto for color, ditto for clarity. Now I'll do it again. A warning. It's saying it's not exactly data frame because we're using dplyr. That's okay. I'll let that pass. It's just going to cast the... So dplyr has its own data frame, which is... You can cast it back and forth. So we'll just let it cast it. That's fine. And look at this. Resampling cross-validation prints out these nice little... text while it's doing it. Oh, I also added measures. I said measure RMSE, because by default it'll measure MSE. So here's the RMSEs. Aggregate result, 0.179. What did I get before? Look at that. It's doing the same thing as I did, except not writing their own code itself, right? Okay, so inside the results, there's a whole bunch of stuff that you could look at. It says we did the diamonds task, we use OLS. It said how long it took. And then you could ask it for the mean and the standard error of each fold. 0.17 plus or minus 0.03. It's about what we got before. If I do this again, will it be the same? It'll be different. It'll make different folds. I could force it to take the same fold by saying, keep the same fold. There's parameters for that. There's arguments for saying, keep the same fold. Equivalent of setting the seed. A little bit different. Again, it's not going to be that much different. You've got 50,000 data points. It's not going to be that much different. Okay. If I made this tenfold, what might you see to these numbers?
What do you mean? Oh.
Instead of fivefold, I did tenfold. Forget 500-fold. Which wouldn't be so bad, actually, with 50,000 data points. So let's go with this one. What would that number be? Bigger, smaller, same? Go.
Would that be the same?
No.
No.
I mean, it could be, but not an expectation.
Oh.
Conceptually, this should not be the same. Good test question, huh?
Isn't it?
Let's just try it. Look at this. Iterations. 500. Play it again. Where's my messages? It's not going to print out for me. There we go.
It'll be less.
There's someone who can take an average, a running average in his head, huh? I think 500 was too many. Now I gotta wait for it to go all the way through. Let's discuss.
Well,
Let's discuss in the meantime, while it's doing its thing, why Moshe is probably right. By the time it finishes, you better have an answer.
I mean,
Oh gosh.
Moshe, what'd you say?
that it's smaller, and I looked at that data. It's mostly 12, 13, 14, 15. But
Cheated. Due to the MLR output. He saw what the edge was going to be.
Wait a minute. I cheated by looking at the historical data.
You cheated by looking at the answer as it's coming in. Yes, when you look at the answer, it's called cheating. That's what cheating is. It's looking at the answer.
Smaller groups will have less variability, we're assuming.
Oh shoot. I didn't mean to show you the other answer too. Why is it smaller? What is this number? What does that mean?
The number of divisions we make on a data set.
No, not K. One of these.
Oh, the standard error of that iteration.
Of what?
Of the out of sample prediction.
Prediction performance. Lower is better, right?
Right.
If I do 500 folds,
Oh,
then I'm leaving out how much of the data?
less.
0.2%. So I'm fitting the model with 99.8%.
So you have both less opportunities for error and more opportunities for learning?
I have more opportunities for learning. Which error went down in my model? You're good at this. Which are the 3 errors?
So you split the data set into more pieces.
He doesn't know, so he's trying to give me a story.
No, I'm trying
Where's
to figure it
Vincent?
out.
Darn. Vincent's my go-to guy for 3 errors. Estimation error. I have more n. Instead of fitting the model with 80% of the data, which is what 5-fold is, right? 4/5. I'm fitting it with 499 500ths of the data. Now, standard error, up or down?
Overall.
No, standard error of these numbers. I realize the numbers themselves got smaller, but they come with a variance. Adriana? No. What's the other answer? Okay, good. Higher. Why should it be higher?
Because with smaller.
Come on.
So you have more standard errors, so it's more difference between.
Oh, you're so close. You have more data to fit the model with, but less data to validate the model with. This is a validation. So SE gets more variable with less data. Like every random variable under the sun. If you have less n, its variance goes up. Variance of x bar, sigma squared over n. Less n, higher variance. More n, less variance, zeroing in on mu. This is estimating the true out of sample RMSE. Less data, bigger variance. More data, meaning bigger test set. Smaller training set, less variance. That's the trade-off of K. We now know it's 0.15 plus or minus 0.09, where before, it was 0.18 plus or minus 0.03. I would rather be in this situation. Why? Why would I rather be here than there?
Because it's more consistent.
What does consistent mean?
Well, it's better to have less variability because then your predictions will be correct more often.
Balance between validation and model.
This is bias variance trade-off, correct? We're going to get to bias variance trade-off in vivid, lurid detail. What does lurid mean?
Pictured, colored.
This is the problem with memorizing GRE words. It's you don't actually know what they mean. You just map a word to 3 words that make sense to you.
memorize the flashcards.
Yeah, I know, I realize. So let me tell you a little story. I was 22, I think. Yeah, and I took the GRE, and I got 800 on math. That's expected. I'm not gonna tell you I got my reading, but it was very bad. I don't know. I just didn't read that much. I don't know, or maybe I'm slow. Who knows? So I decided like this has to be gameable. This GRE thing, the words have to be gameable. So I spent the next 2 years figuring out how to teach vocabulary to high school students. One of those years I spent at a coffee shop in San Francisco, just coding an internet site. Cool life, huh? I lived at that coffee shop. It was on Clement and 23rd. Those are the days. I've had such a fun life. Not even gonna. So much fun. In those days, San Francisco was in such a boom, and I knew some Java and I knew some Python. Cause my first job was Python. That I was able to work like 3 days a month consulting and afford rent and food for the whole month and my car. I made the bare minimum amount of money just to afford rent and food.
So what you do other days of the month? Party.
Did you forget the whole first part of the story?
No,
There was a whole first part of the story. Did that just go woo? Were you listening?
I was.
Sometimes you guys, I wonder about you guys a lot. Okay. Why did I get on this story? What was the point of the story? Oh, the GRE words. Lurid means explicit, usually using pictures and color. But more than pictures and color, it means explicit. We will be going over bias variance trade-off. Okay, now what are we doing now? Okay. So we're taking a pause in this. Okay, we left off last time with cross-validation. So now we're going to do a different problem. So given the same X, the same design matrix with P raw features. What was P raw again?
Red, blue, green. Oh,
Measure.
no.
Guys,
what is P raw?
What do you P sub raw? Why does Jan know the answers and you guys just spit out random words? It's the number of
Categories. No?
Number of inputs.
Yeah, the number of raw inputs that you have. It's the number of measurements you have on each unit. With P raw features, I even wrote features.
It said those categories. Oh, I'm very bad.
No. One of those features may be ordinal with many levels. That would still count as technically one raw feature. And then if you want to linear model it, then you blow it up into L minus 1 dummies. You've seen that, right? Hopefully. That was first midterm, I think. There are many transformations of the P raw features. Someone give me some transformations. Go.
WX or BX vectors, like a linear model, or a linear
Transformation of a single feature.
X squared.
Yeah. For example, the square, the log. I have many choices for each of those features, right? Um, interactions. I can interact features. Isn't interactions fun? Isn't it fun to find them? And see, oh man, there's more to the model than you thought. Right? I always found that a lot of fun. Thinking about interactions, seeing, maybe this with that, and you get more juice. I found, it's like a puzzle. It's like, because you got to use like your knowledge of what's going on, and also, I don't know. That to me is one of the most fun parts. Um, there are many algorithms. This has to do with H. So there are many H's, right? Which yielding many G's. So for example, G1, let's just say, for example, if P raw equals 1, G1 is B0 plus B1x, G2 could be B0 plus B1x squared, G3 could be B0 plus B1 ln x. These are just linear, right? I could make these arbitrarily contorted and nonlinear. So for example, if P raw is 2, I could have G is B0 plus B1 x1 plus B2 x2. G2 is B0 plus B1 x1 plus B2 x2 plus B1 x1 x2. Here's another one you may not have thought of. I could take x here, and I could split it up into little regions. What did I do here?
You made it into a categorical.
Yeah, I took a continuous variable, and I made it into a categorical variable and made dummies for it. Of course, I had to figure out where to split 0, 1, 1, 2, 2, 3, etc. I'm permitted to do that. That means I could take a continuous random variable and turn it into 1,000 features. Can I? I just bin it in little places. Is there anything, am I permitted to do that? Yeah, I'm permitted to do whatever I want. That's the thing about this. There's no rules here. You're just given X and Y, and you just go to town. And you hope you don't overfit. Do you guys agree with that? That's a parable for all of data science. You're given X and Y. And then you could massage X and use whatever this is and whatever that is, and the sky's the limit. There's so many choices. So many choices. So what do you think the question is I'm going to ask?
How do you select correct?
So many choices. So many. So, look, I've got so many choices. So many. These are just linear models with, like, very simple transformations, right? I mean, even identifying a set of models is itself a task. Previously in the class, I gave you the H, I gave you the A. I gave you the X's to put in. Which means I said make this one G. Now I'm saying, like, there's no reason to do this one model if there's so many other things you can do. Right? I mean, we saw in the lab that I gave you the Boston housing data, you fit the linear model, and then pretty much every interaction gave you a better model. We reasoned through them, and we found ones that made sense, but, like, pretty much every single one's going to give you, like, some more juice. In which case, just identifying this set of candidate models is tough. Out of a set of models, G1, a set of, let's say, n models. I agree. Giving you the set of candidate models is another problem.
Is that outside the scope of model selection? Or
Well,
is
yeah,
it
it's.
prediction?
I mean, it is outside the scope of model, because model selection is technically just selecting one of the models out of, or sorry, picking one model to use. I don't want to even say add a set. I just want to say given a set. And this, the wording is subtle, but it does change the meaning. Yes, picking the set of M models is outside this scope. So the problem scope is as follows. I give you a bunch of models, and I say, I want one model to use. At the end of the day, you're going to predict in the real world. You need to predict using one model, right? You need a model to predict with. So I can't just say, here's 100 models, predict. It's like, well, which one do I use? Or what do I do? Do you guys agree this is a good problem? Okay, so again, the whole first part of this class, I essentially just gave you what to do, and you did it, and then you validated that one thing. Now things have changed considerably, because there's no reason to pick one set of P features from P raw features and use one algorithm. There are plenty of things that you could potentially do. So I need ideas now.
Minimize.
Okay, first of all, let's appreciate. Do you guys appreciate this problem? Right. This is a fundamental problem. In statistics. Maybe even in all of science. Why is this a fundamental problem in all of science? Why should chemists or physicists or anyone care about this? Yeah.
For the sake of prediction? Predictive power is kind of universally applicable in terms of when you're taking measurements and trying to understand a system.
You're close.
Is it specifically about the understanding things?
I think so. Yeah, prediction, sure. Oh. I don't know what that is.
Gravity.
Yeah. Newton's law of gravitation.
This has to be some function of M1, M2, and R. Or at least he thought it was. Yeah.
Every model that you make is a statement on relationships, and you're trying to figure out what those relationships are.
Is this the only model for gravitation? Seemed to fit the data, though. Became pretty damn famous with it. We're still studying him 400 years later. This is a model. He selected it. Is it the correct model? Is it absolutely true? Anybody who is alive past 19, no, 1905. What? I think with special relativity, this is already shown to be wrong. Now, I really have to look this up. I used to know this stuff really well. I was a physics minor, so like I thought it was really cool. Then I got to quantum mechanics, and the first day, I asked a question. The professor just looks at me. He's like, "You see this? It's that. And that's that." Like, I'm out. That's it. It's over. I went physics major, physics minor. Which is a really good decision. Because you don't want to be the bench warmer on your team. You want to be a good member on the team. You also don't want to be like the absolute star on the team. And like everyone else is a loser underneath you. So I was in line to be the bench warmer on the physics team. Very much the bench warmer. So instead I left. I went to statistics. Now I'm batting 200. Not Ty Cobb. I get on base. It's cool. They don't just leave me on the bench. They're like, "Oh, you're up. You bat 7, but like, you get the bat. It's cool. We need you." Then the whole class, after the professor did that, he looked at me, and the whole class turned and looked at me. Like, what the hell kind of question is that? About. Anyway. So, which was actually really good because I took all the experimental classes, which is really fun. Like there was this class where we went to the telescope and we took like measurements of like nebulae and like light years away. It was so much fun. Anyway, a lot of fun. Anyway, so look, I think by 1905 they realized this was wrong. Wrong and like that amount wrong, teeny amount wrong. RMSE very small, but still RMSE. Something's amiss. Something's a little bit wrong. Regardless, there are probably many functional forms he looked through, and he found this one that fit really well. So he's like, let's hit it. Right? So there's a fundamental problem in science, because in science you have these phenomenon, like, I don't know, stuff sticks to the ground, and you want to explain it in terms of things you can measure. Here's things you can measure, and you want to explain it, so you make a functional form, you put an equals there. But it could have been another form. There are forms that fit the data better. I'm sure if I put in, I don't know what the relativistic corrections were, but like you have square roots of like the cubic term, that amounts to making like quartic terms, and you get a little bit better. That's a better model. Why not select that one? Maybe you didn't think of it. Okay, fine. What if you did think of it? Why not select that one? All right. So this is a very, very, very big problem. It's an ancient problem. It's a fundamental problem. There's a lot of textbooks written on this. So we're going to study one way to do this. You teach a whole class in model selection. I can't because I don't know it that well, but you could potentially teach a whole class in model selection because it's such a fundamental problem. Okay, what is one thing that you can do off the bat? It seems to like somewhat make sense. I'll give give you 20 models. What do you do with them? Yeah.
Try all the models and compare them.
Sure. Even simpler than that. Don't even worry about trying them.
OS.
No, there are 20 different OLSs here.
Oh, right.
Should be urgency with the square.
That's what he before you guys are too smart. Get dumber. Forget you took this class. Go back to Stat 101. Back to Math 241. What do you do with 20 things?
Just pick one.
Oh, that's you could do that. That's really dumb because you may pick a really bad one. How do you mitigate against that? Picking the bad one.
Take out the ones that don't make sense.
You don't know what makes sense. Why don't you just take the average? Just take the average of all the models.
Meaning, so make a model that is the sum
Yeah.
of all the models in the group.
So model averaging is a, I don't know, good strategy, is a reasonable strategy. If there are 20 bad models, the average ain't gonna help you. But if you have some bad ones and mostly good ones, it's gonna help you. Okay, let's get smarter now. So what did Joseph say?
Check where the
Yes. Here's what we're gonna do. So here's an idea. So you build G1 on D train and estimate out of sample error in D test. Then you build G2 and you build GM. What do you do after that? Juan? I built the first model here, and I tested here. Then I built the second model here, and I tested here. Built the third model here, and I tested here. Built the 20th model here, and I tested here. Yeah.
Comparing with out of sample
And then,
take the flows.
right. So I'll do M star is argmin SE to M. So compute. So select, and then GM star is the final model.
Why is this m+1?
Well, I built the first model, second model, mth model, and then I'm like looking at is the n+1 step. So step 1, 2.
Oh, gotcha.
So step 1. You guys like this? Is this a reasonable thing to do? Why?
Because you're going for the best fit model of your models. Like, we're looking for the best fit.
I could use in-sample statistics, right? Then what may happen if I do that?
overfit.
Yeah, they're not honest. This is forcing me to be honest. Because of not looking at this data. So if I overfit, then I'll see the problems emerge here. Yeah.
Would there be an issue potentially with using R squared? Because if you use R squared, you're looking at a specific kind of improvement.
R squared and SC are 1 to 1.
Okay.
As long as you fix n. So highest R squared, lowest R and SC would be the same. Okay, any problems with this? This is fine. This is a good protocol for model selection. It's okay. Problems for this? Go.
What gets you to one model? Maybe you could use two models together.
Okay, so pick the top 2 models and average them. That's legit. I like it. It's been thought of before.
It doesn't tell you how good that model is.
Yeah, it
Really.
does. You get SC.
Well,
Well, maybe. Okay, why don't we start with what we've already corrected? What's the problem with this setup again?
you sacrifice accuracy for checking.
How many splits do I have?
Okay.
No, I don't have.
Standard fiber.
So one. No,
I have 1 split. What's the problem with 1 split?
it might be.
Idiosyncratic, high variance. So what can I do to correct that?
Make K splits and do.
Cross validate.
Yeah.
Okay. So I don't know how to picture this. So cross validate. So instead of here, build G on D train estimated. Build G on K folds and validate and cross validate on the outer sample. And compute SC from aggregate. So this whole aggregate versus the average of the folds, I think it just has to be that it's lower variance. It must be just lower variance because it's kind of like getting, yeah, that's the answer. So if you're taking the average of 5 folds, I'm going back to the point that I made in the beginning of class now. If you're taking the average of 5 folds, each of those folds is only from 1/5 of the data. If I use the aggregate, it's like I'm getting 100% of the data. I'm not getting 100% of the data because a lot of the data is dependent, but I'm getting more than 1/5. So it must be that the aggregate metric is less variance. You know what? I don't know. I have to look at that. It probably has something to do with variance. It probably is just less variance. Okay, I'm never asking that on a test. And in real world, they're going to be about the same. The average of the folds versus the aggregate in a cross-validation. So whatever. Just instead of from aggregate, write whatever you want. Write aggregate or average of the folds. Okay? Deal? I'm sure someone has thought about this and written up on it. Because someone's thought of everything and written up on everything. It's a very crowded space. There's a lot of data science and statistics professors out there. And they're all teaching the same thing. So when they teach something and they get to a certain point, they're like, I don't know. And some of them actually take the initiative to say, let me figure it out. And then write it up and put it on the internet, put it in a journal. That's usually how it goes. Cross-validation was invented in the 1960s? When was that guy? When was that paper? Maybe 1974?
Whatever. It's a long, long, long time already for a lot of people to think about these fundamental issues. This cross-validation is not a new idea. It's not like some guy at Google thought of it, right? No, it goes back to at least the 70s, probably the 60s. We're going to be doing trees probably after the break, maybe even Thursday. Trees go back to the 1960s as well. Became popular in the 80s. Model selection, man, that goes. People were talking about that since the beginning of time almost. It had to be because no one. Like, how do you pick a model? Okay, where are we? Okay, so we're doing the same exact thing, except we're just rotating this thing, and then we're looking at the average or the aggregate out of sample throughout the 5 folds. And all that's going to do is do what?
Reduce idiosyncrasy.
Yeah, reduce variance. Variance is bad because if all these numbers are really variable and you pick the lowest one, it could be the lowest one because it's actually the lowest one, or the lowest one because do I have to go back to Math 241?
Can you repeat what you just said?
Okay, all right. Seven models. All right, I just did this with 7 models. And there's your RMSEs. Cross-validate out of sample. Sounds good? You guys like that? What's my best model?
First one.
First one. Good. First one. I agree. That's the lowest number. The number 1 corresponds to this index. Ship G1. Fine. Now, G1 could actually be the lowest error. Like fundamentally so, in an expectation sense. Or I could have just gotten lucky. Why not this one? This is number 3. Maybe this one's the best. But because of random variation, that came 109, 1.9, that became 1.7. The variation is so big, then all these models are as good as equal, because it's just like, it's like the guy in poker. Like, is he really the best at poker, or do you just get good cards? What's the answer to that question? Maybe both. Or the real answer is you don't know unless you really see these guys duke it out, like for thousands of games. And after thousands of games, guess what? Everyone gets the same cards. You've margined over and integrated out the effect of lucky. There's no luckiness there because everyone was equally as unlucky as lucky. Then the real winners there, consistently over thousands of games, will be the best players. That's the overall mu average. But poker is notoriously large standard error. Right? Who hasn't been dealt 2 aces in the hole and then like takes the whole pot, even though they have no ability? That's happened to me a bunch of times. More often than not, I lose, but it's happened to me a bunch of times. So if you're measuring just based on those few plays, it's like he's the best, clearly. So you have a problem here. Like if these are high standard error, you're just gonna be guessing. This is as good as random here, right? Because the standard error is so high that it's actually swamping out the signal. There's so much noise, there's no signal here. So you want these to be low standard error, which is why you want K to be low. You're okay with the bias, right? K should be like 5. You don't want to be too biased because K equals 5 or K equals 10 is good. The more models you put in, the more accurate this will get, or less accurate. If your goal is to find the best one, and you put a whole bunch of in that all look the same, you're just going to be picking one. They're all going to look the same. You're not going to be able to find the best one. Okay, So that is a good reason to use cross-validation, because it'll reduce the standard error. That's a win. Okay. We seem to always be running out of time. Maybe because I'm telling too many stories. Telling too many stories. I did this this morning too. Who was here this morning? I told too many stories this morning. I'm getting less done. I need to get more done. Still something wrong with this. Not wrong, but something that's left to be desired.
Restricted to a specific set of models? I don't know.
No. I agree. Given that you've got M models, we're working with that. Picking which models to use, that's a whole other problem. Model selection and picking the candidate set are problems that machine learning really solved. So you can see how complicated models get really quickly, right? They get really complicated. And you want them complicated because you want to reduce which error?
Misspecification.
Yes. So you want them complicated. But there's so many different complicated models. So which one do you choose? You need to do model selection on those. So we need to define how complicated it is, not overfit, because if you overfit, then any gains that you get with your misspecification error reduction will become losses in estimation error. And you'll shoot yourself in the foot. So you got to play that game. I want it complicated, but not too complicated. Then I want to pick the right one. See how hard this is? Not easy. Okay, there's still something wrong with this. Not wrong, but there's something that I'm missing. What are you missing? Go.
Extrapolation.
What do you mean by that?
Assuming that our current data looks like, assuming stationarity, thank you. We can also assume that the data that we're plugging in looks like the data that we have, meaning that the test data looks a little bit similar to the training data. And that doesn't give us a good metric or idea of how, it doesn't give us a good metric of how we extrapolate.
You're using the wrong words. That's the problem. I think you have the answer, but yeah.
I'll put it this way.
Outliers?
Okay, as M gets large, how does SE M star behave? Okay, SEM star is the best one, 1.7. I'm getting the best out of sample error. That's the whole. That's the name of this game here, right? Give me the best out of sample error. 10 models. Do the cross validation. Give me back 10 SEs. Pick the lowest one. We agree on that so far, right? That's agreed upon. Make it 100 models. Okay, go cross validate. Get 100 SEs. Pick the lowest one. Give me 1,000,000 models.
That's very computationally expensive.
Did anyone take 621 with me? No. Some of you will be taking 621 next semester. Connor, you ready for more? 621?
Not yet.
Oh, come on, Connor. Next semester, 621 will be a bonanza. If you like 341, man. How does you, 621. Jan didn't take it with me. He took it part with me. You audited for a while, I remember.
Yeah.
How does the minimum of a whole bunch of random variables behave? I'll put it this way. What is the theoretical lowest RMSE can get? 0. So we've got a whole bunch of random variables with support 0 to infinity. And I take the minimum of all those random variables.
It'll probably be an extreme, I know.
Minimum will be extreme, that's true. What's the most extreme it could be?
0.
See that?
So you might select an overfit one, you're saying?
1 second. Let's appreciate this for a moment. If I take 100 people and ask who's the tallest guy, okay, maybe the tallest of 100. Take 1 million people, you're not the tallest. 10 million people, 100 million people, 1 billion people. It's gonna get pretty damn tall. Right? If I take 100 billion models and calculate the RMSE, it's gonna be pretty damn small. It's gonna get to 0.
As n goes to infinity. That's okay, that's okay. Okay, look. It goes to 0. You're still picking the lowest one. Right? Which is your yardstick for the best one. Now you'd argue, well, if you have 1 million models, like, come on. And you pick the low, I mean, they're gonna all look the same, so you're really picking among equally modeled. Fine, oh, they're all equally in performing. Fine, that's okay. But what does that final SEM star fail to tell you? Which you may want to know.
Like
How much what?
better.
You're very close. You guys know this.
How much variability there is? No.
That's a function of number of folds. Okay. Well, let's do a simple empirical exercise. This is 100 models. The lowest RMSE is 1. 1,000 models, it's 0.2. 10,000 models, it's 0.1. 1 million models, it's 0.01. It's going to 0, right? Is there any value in that number other than that it allows you to select the best one anymore? All it becomes is a comparative device. This model is better than that one is better. I mean, modulo the standard error. But does that number in an absolute sense mean anything anymore?
Depends on the future.
You guys need to know this. I can't just give you the answer.
But why doesn't it just means that's the standard error of a given model? No? You're saying eventually you'll start to rely on more idiosyncrasies?
How do you know you didn't have
Okay. What does SE represent again?
Because this is out of sample, I see.
It's out of sample SE. That's out of sample predicted performance. What is that? What did that answer in the beginning go back to, like when we started this whole project?
Whether or not we were trying to gauge what
Trying to gauge what?
the effectiveness of the model.
The performance of the model in the future.
Right.
The question was, how well will this model do in the future? Answer, SE. Out of sample SE. If I could arbitrarily drive it to 0,
But it's
how
not.
can that metric be used to predict?
thank you, Joseph.
But why? It's
That
not
wasn't so hard.
arbitrary. It's entirely.
I can
consistent with the model.
arbitrarily drive it to 0. It's a fact of Math 621. As Jan said, the minimum of a whole bunch of random variables gets really small. And as m goes to infinity, it'll go to 0. It's the same thing as overfitting, right? I could just make up a model that'll fit perfectly on the out-of-sample data. I'm bound to find it, right? Aren't I bound to find it? You go through enough things, something will fit, right? So there's a key on this, on that door over there. I try my key on it, it's not going to work. I try your key on it, it's not going to work. I try all the keys in the world. I will open the door. The door will open. One of those pin configurations will be the same. It's not that unique. Why did I spend so much time on this simple point? Tell stories again. I should have just said the answer and moved on. Which means we need what?
A better metric to use for future data.
Vincent would know the answer, because he's done this before. Can someone call up Vincent and tell him to get over here in the next 10 minutes? Like, Vincent, we really need you. I know you're sleeping, or I know you're but we really need you to come. How do we get around this whole honesty problem in the beginning?
Oh, well, we don't use all K folds in each
There we
individual one.
Say that again?
You don't
Here's
use,
what we're gonna do.
or you don't use the same K folds in each individual one?
Or devalidate. We introduce a third split. Previously, we had two splits: training and testing. It was simple. You train here, and if you did one model, then the out-of-sample error here would be honest. That's where we started the project. To get better, we flipped it, we crossed it. We moved the folds around. Fine. That made it less variable. Fine. Here, we can no longer do that anymore. If we want to actually answer the question, how well does my model do in the future? Then, if I use this setup, I'm not being honest, because I'll eventually find something that's over.
You're gonna fit your test data.
I'm going to fit my test data. Exactly. So what I'm going to do is I'm going to do this procedure, but only call this procedure detrain and deselect. I have a training set and a set on which I use to select the model. That's that thing over there. Then once I'm done doing this, whatever I do in here, the cross-validation, then I say, okay, I found GM star, test here, give me an honest, this gives me, so this selects the model. This gives me the true SEM star. The honest. The SEM star I get from this is not going to be honest anymore. It just happens to be the lowest of the thing that I found. And that could be just because I've tried enough things and eventually I found something, the key that fit. It's kind of like overfitting. Once I'm done, I open up the lockbox, I look at this, and then no more peeking. Otherwise, you invalidate that. If you think about it, it's the same exact thing we did in the beginning. Imagine I call this the D-train, and I fit some model on it. And then I say, how's the model do in the future, and ship it. Except, this whole procedure is a wild, crazy ensemble craziness of programming where I'm actually trying like millions of models and seeing which one is the best. It's still taking this data and fitting one model on it. Right? Isn't it? This whole thing looks like I'm fitting 100 models. But at the end of the day, I just get one model. So I've taken the data and I've converted it to one model. Then I say, how will that model do in the future? Same exact thing. You guys like this?
I feel like there's a lot of implicit problems there that you.
What is the implicit problems?
You repeat the same issue. If, let's say, obvious question number one is, what happens if you have a bad SEM star? Then you have to go back to the drawing board, but
This
you've
one's
already locked the lockbox.
This one's bad.
That you've done your selection, and then you finish that, and you do that test of your D-test, and it's bad. You've overfit.
Too bad for you.
Right, then.
Sucks for you, sorry.
So then.
You've overfit. Yeah, that's called overfitting. Same exact thing as
But
before.
is there some process of
No.
reselecting that? Because
No.
then you'll just end up overfitting again.
Yeah.
So what do you have to shuffle your data? But eventually you're going to overfit
No,
your data.
no, you can't. No.
So that,
At some point, there's this thing called reality. You're yay tall, and that's it. You make yay much money, and that's it. That's too bad. Your 4G is yay fast. That's it. Your car can go yay fast. That's reality. There are limitations on reality.
So you
This is a limitation on reality. If If you are irresponsible, you'll overfit, and then your model will stink. It's too bad. You should have thought about that before you tried a million different models that overfit, or whatever you did. Maybe not a million models, just try 20. Don't put in every single feature. Don't put in every interaction. Don't put in every square term. Because each of those is a new model. So, yeah, if you only have 100 data points, you cannot try 100 models. You're going to do something wrong. Yeah, there is this thing called reality. Data science isn't magic. I was just having this discussion at UPenn when I gave a talk there. And one of the professors, like, he really consults, like, a lot. Consults a lot. And he says that he goes to clients, and the clients think he literally, like, waves a magic wand. I'll tell you a story again. And that he just does magic. It's not magic. You use features that correspond for causal mechanisms. They'll probably do well. If you don't try too many things, you won't overfit. It's not magic. But there are limitations on reality. This is a limitation on reality. Okay. Yeah.
So the validation of dtrain and deselect, you're comparing the X.
Deselect and devalidation are the same thing. It just I don't know why some textbooks call it devalidation. I like to call it deselect because you're using a piece of the data to select the model. So inside this procedure, you're evaluating a whole bunch of models, n models, and you're using this piece to select the best one.
Okay.
But because of this phenomenon over here, whatever error you get on this selection is not going to be honest. Now, if you only test a few models, it'll be mostly honest, right? But the more you pick, the less honest it'll be, which is why you leave this one out, leave this piece out, and do that in the end. Okay, so select the model. So this whole thing is cross-validated. Now, what you can do at the end is you can cross-validate this whole thing. You have 2 loops of cross-validation. So here's outer fold 1. Here's d-test. And then inside here, you're rotating through, cross-validating using deselect. You're rotating this around. And fold 2 over here. Here's d-test here. And then this thing is rotating this around. This is very hard to draw, but conceptually it's very simple.
Like deselect, you move the whole block over there.
Deselect, this and this are the same.
But aren't you cross-validating with the whole?
Yeah, I'm moving this around,
Okay, yeah.
right?
Okay.
In this picture, I'm moving this around, and each time I'm getting the aggregate for deselect. Then once I'm done, I select the model, then I test just in this chunk. That would suffer from just what we said before, that this split, this and this split, this is one split between this and this. It's idiosyncratic. I would want to move this around too.
So you'd be now shifting between 3 categories.
Right. So inside here, I specify the first fold of d-test, and I do the cross-validation in here. And I specify this, I do the cross-validation here. Each time I get an m star 1, an m star 2, an m star k. Now this is hard. Again, rather than like writing essays on the board, we're just going to have to talk this out a bunch of times. Because it's just going to become a lot of text, and I'm just going to... Each time you rotate the outer fold, this is the inner fold, the inner CV, and the outer CV. The inner CV is for the
moving the select around. The outer CV is moving the test around. Each time you do that, you get a different M star, which means you get a different model. So you can have K different models here, potentially. Because it may select a different one, especially if it's all modulo standard error anyway. So then what does the SE of the test once it's cross-validated represent? This is like hard. This took me a while to wrap my head around. Literally wrap. It's two different wraps here. It's like
Like SE of the outer cross validation.
yeah.
There's also variation in that.
Sure. Forget about the variation. Imagine it's real. The answer is 2.3. What does that 2.3 mean?
The average SE of a given model. So that's like, no?
No. Yeah.
Like the variation in like the model that you chose versus like the other potential models that you chose.
Hold on. This thing represents predicted performance of a model.
Yeah.
Which model?
The one that you picked. Based
But I
on
picked
the
5 different ones.
based on the full.
But I picked 5 different
Oh.
ones.
Are you rotating between different models? Or are you rotating between the
Alright,
data
let's look
set?
at this. Let's look at this, right? Just look at this fold. That's this picture here. I'm cross-validating this and leaving this constant. Right? Once I get to this one, I'm moving d-test, and then I'm splitting the other one between d-train and d-test, and doing the same thing, and doing the same thing, and doing the same thing. Imagine 2 different for loops. MLR does this nice, supposedly. I'm still trying to figure out how it works. This is actually... I'll eventually figure it out. It's supposed to be easy, but I can't seem to do it.
So what's the outer loop cross validation doing?
The outer loop is fixing the following issue. It's saying the predicted performance of the model is just on one split. So it's high variance. It's getting to be lower variance, so I cross-validate.
What's our question?
Alright, so in here, I'm picking a model based on the best. Let's say it's let's just give it numbers. There's 20 models, third model. Over here, I now have a different split. So when I split this up and I run my 20 models again, this may not be the third model anymore, maybe the 7th model. This may be the 10th model. So I wind up with the third model is the best, the 7th model is the best, the 8th model is the best, the 1st model is the best, the 14th model is the best. But this is not saying which is the best model, it's saying what's the RMSE, the predicted performance of whatever. And that whatever is going to be the whole procedure of model selecting among the 20 models. The procedure itself selects a model. When you do this outer loop, you don't care what the model is, you care about what the procedure gives you. It's saying, what is the predicted performance of that procedure of the model selection? Not a specific model. Because that procedure can give you a different model each time. Yeah, I know that's hard.
Oh, yeah, and then you would take like maybe the mode of it? The mode of whichever model it's selected?
Oh, okay. The final step then. Okay, I wish Vincent was here. The final step is you build. Once you get this, you say, I have an honest estimate of how it's going to do in the future. Then you build the model on all of D, and you ship that. That's your final model. Building a model on all of D would be doing this. And shipping M star. And then you'd actually get one of the 20. Yeah, this isn't working.
so well here. We gotta just, next class we have to just do it again, and then again and again, until it like sinks in. Maybe see it on the computer. Is that the right code for that? MLR should be able to do it. I'll figure it out, don't worry.